Okay, welcome back everybody. Moving on to the second half of section 5.4, we're going to be trying to find eigenvalues and eigenfunctions, really just by an example-focused class today. Instead of having really powerful theorems, we don't really get anything quite so powerful for these, just because all of these equations will reduce to, either an ODE or a PDE at the end of the day. So there's not much theory that can go behind it other than the entire wealth of PDEs and ODEs knowledge. So with the intent that sometimes these are slightly easier problems to solve than maybe some of the really difficult ODEs and PDEs. So that's what we're going to run into today, but primarily examples focused. We're going to start with this proposition though, which I just call finding eigenvalue eigenfunction pairs. I don't even know if you should call it a proposition. It's really a restatement of the definition, but I do want to make it like a clearer statement for you, the viewer, reader of this book, to really make it clear that when we try to find these pairs, we are just analyzing the following conditional equation, conditioned functional equation. So we're just writing out the eigenvalue equation itself, and then we're also making sure to condition the function or the solution to the eigenvalue equation that it is actually in the domain of the operator that we're looking at, right? So this is where the domain, like I said, always plays an important role. You always have to condition your eigenvalue equation on the solution actually being in the function space you care about. That's it. That's all the proposition is going to say. So with that said, let's actually get about solving for these Legendre polynomials that you experienced in the last video. Let's recall, what did our operator look like? It looked like a derivative in x and then multiplying x squared minus 1 and computing another derivative in x. And our domain here, V, was the space of functions from the interval -1 to 1 into R, so that the limits on both sides actually existed. So what is this equation going to look like then? What is our eigenvalue equation actually going to look like here? We just write it as the following. It's that you take L, and then you say, I don't know what the function is. I don't know what lambda is, and I still don't know what the function is, but there was L on the left. And then I'm also going to condition my equation on the same conditions that are in V. And, there should be a space right there. It's kind of poorly typeset, but we're asking for both of the limits as x goes to -1 and +1 to exist. So this is always our condition. You always include the condition that's involved in the domain, in the actual eigenvalue equation, and then you actually solve the specific eigenvalue equation as well. So how are we going to solve this? Well, what we have to do is solve this particular ODE, where we don't know why. We kind of know lambda. We pretend like we know lambda. It's just some constant that's sitting around. But that's an ODE. So we have to kind of go back to our ODE's knowledge. And we see that it's a second order linear, but polynomial coefficient ODE. So we can't use kind of our favorite second order constant coefficient work on there. We have to be a little bit more clever. The method of power series is kind of the one to go to here. Why should it be a good choice? Well, power series and polynomials interact really, really well together. So that's why we're going to use the method of power series to solve this, which basically just means we assume that our solution is a power series. Not really terribly surprising to assume that our solution is a power series when we know it is certainly differentiable. But we'll go ahead and assume that it's a power series, and then what we do is we grab this power series and we plug it in right here. We plug it in right here. So this is a little bit of ODE's knowledge. It should all be coming back to you. We plug it into both sides. We actually have to compute then the operator on all of these x's, and we can just pull a lambda inside if we want to. That's not too terribly important. But computing the operator on all those x's is kind of the tricky part. What happens is, well, there's two total derivatives happening. So some of the terms had two derivatives taken. They each give out an n and an n-1. And then there's a multiplication by x squared minus 1, which is, I've simplified to 1 minus x squared there. For some reason, I took a negative of both sides here. That's okay. And then there's also going to be, really because of the product rule. So because of the product rule, you're also going to get one term where you've taken a single derivative, which is going to give the n and n-1. And then the product also changes an x squared to a 2x. So that's why those terms are there. And then you need to re-index everything, right? So we really want to compare not a bunch of x's to the n-2, n-1, and n together. We want to compare everything in terms of x to the nth power. And so if you go back to an ODE's course that covered a power series method, you just have to re-index everything at this point. And all that's going to do is it's going to shift the subscripts in these c's and maybe shift a couple of these n's around. And what we end up getting is an n+2, n+1, n+2, n+1, and n. And then the right-hand side is still just lambda cn. Power series method then says we're going to compare the left-hand side to the right-hand side, the non-x terms, and we set them equal to each other. Once we set them equal to each other, we can find a relationship between the n+2 term and the n term, and it's just given by whatever the relationship actually is. What's important now, though, if we continue on the power series method, is that since this varies on every 2 steps, it makes sense because it's a second-order differential. then we actually have 2 degrees of freedom at the beginning that we can choose either C0 or C1. Choosing C0 and C1 to both be 0 is a bad idea because it's going to force everything to be 0. So we need at least one of them to be non-zero. And that can be somewhat arbitrary. You find out that if you wanted to solve this in closed form, setting C0 or C1 non-zero, you get the following choices for Cn. And that's why it depends on either C0 or C1 when n is even or odd, just because it jumps every 2 steps. So starting at 0, you jump it by 2, you get 2, and then 4, and then 6, and so on. And that's why we have a split between the evens and the odds, depending on C0 or C1. What we get here is some product notation nonsense, right? So here's a nice little product notation, which recall just is like summation, but for products. So you're just doing a lot of multiplication instead of summation on these notations here, and each term has a lambda inside of it. Now, you can take these CNs and you can put them in to your solution, but you're going to find out that because of this lovely boundary convergence problem right here, that we're forcing that the boundary exists, we actually have a huge restriction on the lambdas that are going to work for us, because what's happening here is that these products grow like n factorial squared. And so when they're growing like n factorial squared, notice in the denominator there's just a single factorial. So where we really have n factorial squared over n factorial, or rather we've got something like n factorial here, well, the ratio test is going to say this does not converge if there are infinitely many c sub n's. Okay? So what we actually need is that one of these c sub n's becomes 0, and that's only going to occur if one of these terms is 0 for some lambda. Right? Keep in mind, lambda was the set of eigenvalues which we don't know yet. The boundary conditions will give us knowledge of possible lambdas. So that's the whole reason why boundary conditions exist in these problems, is that we start out saying lambda could be whatever we want it to be, but we find out that the solution only exists, especially under some boundary conditions. The solution only exists for a very particular set of lambdas. So in this case, we find out because of the ratio test that we're going to converge on those boundaries if and only if it eventually equals 0. Well, if it eventually equals 0, that means that lambda will eventually equal 2j times 2j plus 1, or 2j times 2j minus 1. And therefore, the only allowable cases are when these are 0 eventually, which actually means that lambda is eventually equal to, or actually lambda has always been equal to, n times n plus 1. And this is where we find eigenvalues all of a sudden pop out of our equation. It's when we apply these boundary conditions that we fix specific eigenvalues. And so now that we know that lambda has to take those values, we can just say, okay, now suppose lambda does take a value n times n plus 1. Let's actually figure out what this sum is equal to. And it turns out to be a polynomial. Since Cn becomes 0, this is a polynomial of degree n minus 1, and that polynomial will look exactly like this. Or I guess it's n plus 1 minus 1, which equals n. But yeah, the polynomial looks exactly like those. That it does equal those is maybe a bit obscure for now. You actually have to calculate it all out and verify that the two are equal to each other. This is something for another time. I'm not really going to waste too much time on it. But the polynomials do take that form, and those are the Legendre polynomials. So we can do the same thing with the Bessel functions. That was kind of the second example in our previous video, where I said I had this operator, and my space was the space of entire functions. That's what this means. The derivative exists everywhere in the complex sense. It means entire functions. And so we're going to go ahead and set up our differential equation, eigenvalue equation, where I don't know y and I don't know lambda still. So that's an unknown, lambda's an unknown, and y is an unknown. But I'm going to try to solve this differential equation and see if I have any restrictions on lambda. And then in particular, my boundary condition, or my external condition, is that the derivative exists everywhere in the complex sense. Well, I can go ahead and try to solve this equation the same way I did before with the power series method. It turns out in this case the Frobenius method is going to be to my advantage, and that's just because I've got these x squares sitting out front that there's a good chance that my solution is going to have to be multiplied by a higher power of x. So that's just called the Frobenius method, where you give yourself kind of this extra availability of having alpha in the integers, in addition to your regular power series. And if we go ahead and grab this power series and plug it in here, what we end up with is the following differential equation, where there's my operator L, and then I've plugged in my power series, and I've plugged in my power series, and then I actually have to compute L against all of these x's, and I can pull lambda inside. There's lambda inside. If I compute L against all these x's, I get this lovely giant term here, and that's okay. But what I have to do is actually calculate everything out and then re-index it, so I have things only in terms of x to the n plus alpha power on both sides. What's nice here is that this minus 1 times that cancels with that, so I really do have quite a few fewer terms than I started with on the left-hand side. I end up with n squared cn plus cn minus 2 on the left, and then a lambda cn on the right. So once again, I just compare these together. They still have to be the same, and so you say they're equal to each other. What do we end up with? We end up with cn minus 2 is this coefficient against cn. Now what's really important here is that entire power series have no non-negative indexed entries. That means that there's no such thing as c negative 2, no such thing as c negative 1, so those both have to be 0, which means that when I plug a 0 in here and I get a negative 2 there, then I need to be equal to 0. That's only ever going to happen if lambda minus alpha squared is also 0, or perhaps c0 is 0. If lambda minus alpha squared is 0, that means lambda is alpha squared. Now all of a sudden, I have restrictions on possible lambda. So no longer any possible lambda in the world, they all equal alpha squared. Keep in mind alpha was in the natural numbers including 0 by way of the Frobenius method. So now I know that the only possible lambdas here are the square natural numbers including 0. In the case where I'm working with the odd terms instead of the even terms, I have alpha plus 1 squared, but of course every natural number squared is equal to another natural number plus 1 squared, just by the definition of natural numbers. They are equal to themselves plus 1, except for 0. Okay, so that means that we are going to assume that lambda takes one of these two values. It can't equal both, but it can take either of the two of them. And let's just assume that it takes the alpha squared one, which means that c1 has to be equal to 0, because then this still has to be true. So let's say lambda is alpha squared. What I can do is jump back up to here and put an alpha squared in here. Now that I know that lambda has to be alpha squared, I can rearrange this to say that cn plus 2 is equal to 1 divided by alpha squared minus n plus 2 plus alpha squared, all times cn. So there's a nice little relationship between cn and cn plus 2. And when you calculate all of these terms out, what you see is that cm, this is for specifically n being the evens, so 2m, is equal to your initial condition times negative 1 to the nth power, 2 to the 2m, m factorial, and n plus alpha factorial. So I'm just writing out the recursion relationship and actually solving out for what it should be, which means if I plug that in to my power series, where keep in mind n was 2m because I'm only working with even powers, I end up with the power series given here, which is exactly the Bessel function power series. And I also found out that my lambdas were alpha squared. My eigenvalues are alpha squared. So this is how, in 2 ODEs problems, you use the power series method to obtain your eigenfunctions and eigenvalues. So if we move on to really a PDE's version of this, right? The other two are ODEs, so an older course should have been enough to cover this for you, but the version with the Laplacian is definitely what we've prepared for in this course. We're now going to calculate the eigenvalue eigenfunction pairs of this particular negative Laplacian over our domain C0 infinity of the square 0 to pi squared, right? We did cover this in the last video. What is this domain? It's functions from the square to r, where we have infinitely many derivatives, but more importantly, the value of the functions on the boundary is 0. And that's really important. That's going to show up in our PDE. So what we end up getting when we're looking for these eigenvalues is a PDE with boundary values, right? So we have a boundary value PDE here. That's all we're going to be trying to solve. Now, how do we want to do this? First thing we have to ask ourselves a question about is what sort of a space are we working on? Can I use Fourier methods? Well, probably arguably you could use Fourier methods, but this doesn't take the form of any of the Fourier methods we studied in this course, so we won't be using this course's Fourier methods. Instead, we have to result on our very last section in chapter 4, which was separations of variables. So we're going to really be stuck with separation of variables here just because we can't use a Fourier method the way it's been presented. So let's try to solve this problem with the separation of variables, and all we have to do is start with the ansatz, right? Separation of variables ansatz. take one function of x and a function of y and multiply them together. Then when we compute our Laplacian on that, we're computing a partial x on the two of them and a partial y on the two of them. So the x is only c phis and the y is only c psis. That's step one in separation of variables. If we rearrange everything to be only a function of x on the left-hand side, then the right-hand side becomes only a function of y plus lambda. And that is totally okay, because now in step 3, what we can say is that they're both equal to a constant, because this only depends on x, this only depends on y, so they must both be constants. And that gives us two ODEs that we can solve. What's really nice about this, it's just two second-order ODEs, and everybody knows how to solve second-order ODEs. However, I do make a little assumption here. There's a mu, there's a lambda minus mu. We make our lives a little easier by just defining alpha squared to be mu and beta squared to be lambda minus mu. If that's the case, then of course adding the two of them together, we can recover lambda just by saying alpha squared plus beta squared. So we're not losing any information by making this change of variables in mu and lambda, but what we are going to do is make our life a little bit easier when we calculate these solutions. So just by making those little relabelings, we immediately recover solutions because it's second order constant coefficients ODE, and we get cosines plus sines of this particular frequency, and we get cosines plus sines of this particular frequency. So those are going to be our two solutions, which means that our original phi, right, phi of x and y, is the product of phi of x and psi of y. So I grab that, plug it in here, grab that, plug it in here, and then it's technically a superposition of all of those, right? So here's my superposition of the product of all of these solutions in both x and y. Now I have to ask myself the question in particular about meeting the boundary conditions. Now I must meet the boundary conditions. Well, what do I have to do? I have to evaluate them on the boundary. So if I evaluate at the boundary x value of 0, then all of the c2 disappears and the cosine disappears. So I'm just left with c1 of alpha equals 0, and then times a term that I don't want to be 0. So that means that c1 of alpha must be 0. If I evaluate at pi, knowing that c1 was 0, now I have c2 of alpha times sine of alpha pi has to be 0. That immediately tells me that c2 of alpha times sine of alpha pi has to be 0. And in fact, I'm probably not going to want to make this term 0 because that would just kill everything off. So what I need is actually that sine of alpha pi is 0. And for sine of alpha pi to be 0, I immediately recover a restriction. This is where my first restriction on lambda comes from. I just found out that alpha needs to be in the integers minus the value 0. I do the same thing with the third boundary condition, which is now in the variable y, and that tells me that d1 of beta has to be 0. And then my final boundary condition, which is evaluating at pi in the y direction, says that d2 beta times sine beta pi has to be 0. And I don't want d2 beta to be 0. That would kill everything. So now I need sine beta pi to be 0, which just like before says beta is in z minus 0. And so now I have my two restrictions, right? My early restriction was alpha was in z set minus 0. Now I have beta as well. And recall, way back, lambda is alpha squared plus beta squared. So the only possible eigenvalues are alpha squared plus beta squared, where alpha and beta satisfy these properties. So there's where my restrictions come from. And then, knowing that all of my lambdas take this form, what else do I know is I can just calculate out what does c have to be, the c star of both variables have to be to actually match any given lambda in the eigenvalue equation, right? So I'm just computing the negative Laplacian of this, negative Laplacian of this. You find out that you know the c's just have to be some form of a constant times sine alpha x sine beta y. So those are going to be your eigenfunctions associated to lambda equals alpha squared plus beta squared. And the alpha and beta can only be in z minus 0. So that's how we do this with regards to PDEs. And I have one quick proposition that does talk about point spectra for second order linear constant coefficient PDEs. We can gain an inclusion or a subset of the point spectra of some second order linear constant coefficient PDEs just by starting out with our operator here. So suppose this is my operator and everybody's like, what's the domain? Okay, because you care about the domain, right? So the domain here, as long as we just give ourselves basically free reign over the domain, then this set here, where all I've done, this is really me producing the quadratic form. And you should recall, this is like from the classification of second order PDEs. or also recall it from the Fourier multiplier. It's all kind of the same. What we're doing is we're replacing every gradient here with a vector y. And then we're asking ourselves, what is the range of this quadratic form when y is allowed to be in the d-dimensional complex numbers? Whatever is in there has to be in my point spectrum. So there's a nice little proposition that says we can actually calculate the point spectrums of these constant coefficient PDEs fairly easily. We at least get a subset of the point spectrum in there just by replacing the gradients with y. And the proof is not hard at all. You just assume that your eigenfunction takes the form e to the y times x and calculate out what lambda would be in that case, and it's exactly what you're looking for. So you do get that subset right away. And this does extend to actually nth order linear constant coefficient operators. So even if you represent your PDE in the nth order as the following, you can once again just replace the gradient with a vector y and let it range over all of d-dimensional complex space. Keep in mind, what's the domain, Evan? This is the least restrictive domain. If somebody gives more restrictions on the domain, then you're going to have to be a little bit more clever. But under a very, very common super unrestrictive domain, you can find these particular values in the point spectrum at least. And that's just by including, you just choose these functions to be your eigenfunctions. Now, with that said, I will provide this final example that's like, hey, what if I just want to find a couple eigenvalue eigenfunction pairs for a linear constant coefficient PDE? Here's a lovely linear constant coefficient PDE associated to the domain right there, which is the least restrictive one. Hence, proposition applies. What I can do is just grab a couple examples of E. This is really E to the 1, 1, C dot xy, right? So it's a nice little dot product of one vector against xy. Call that my eigenfunction. Go ahead and calculate it out. You're just doing the gradient calculation, a matrix multiplication, the divergence calculation, and you just end up with, what do you know? This was an eigenvalue of 1 for this particular operator. If you decide you want to do it with maybe a different function, all of these should just be exponential functions of linear, right? Exponential to a linear function of x and y. Then you can calculate it out again. And what do we get when we choose a different linear function of x and y? We get an eigenvalue of -1. So it's just like a nice little way of finding a cute collection of eigenvalues and eigenfunctions for linear operators with constant coefficients. Unfortunately, a lot of the ones that we run into will not be that easy, and especially, this domain will not be quite so unrestrictive. But I just wanted to provide an example, just give everybody an idea of what we're looking at. Anyway, that finishes this section. Really, we're getting into the spectral theorem next, which is we're going to place a huge restriction on the operators we can study, but what we're going to gain out of that is knowing exactly when they're diagonalizable. So we'll get there next. See you then. Bye.